All right, let's look at some problems in chapter 12. Let me get my pen working. Chapter 12, and we're going to be on page, well, it's a horrible 12, isn't it? Chapter, and we are on page 388. We're going to do, first problem we're going to do is number 10. Okay, it says a barrel contains a 0.120 meter layer of oil floating on water that is 0.25 meters deep. Okay, so we got a barrel and we got a layer of oil here. Okay, that right there is oil, and the layer is, and I probably could have made it thicker because the barrel's not that deep. Let's fix that. Try to keep it to scale here. It's almost half of it. Yeah. So, okay. And this is oil, and this is water. Okay. And the layer of oil, let's see, this is 0.120 meters, and the entire depth of the barrel, 0.250 meters, okay? All right, and the density of the oil, rho of the oil, is 600 kilograms per meter cubed. Remember, we always have to do that. It says, what is the gauge pressure at the oil-water interface? All right, so we want to know what the pressure is, and this is going to be pressure gauge at the interface, okay? All right, well, we know by definition, and if we look in our text, yeah, we can look at a couple equations, 12.16. I can't remember what page that's on, but I'm looking at the end of the chapter. So we know that the absolute pressure is equal to the initial pressure, atmospheric, plus rho GH. In other words, the pressure, at a particular depth, okay? All right, so let's rearrange our equation. What will our equation look like? Well, it'll be like this. It'll be the initial pressure minus the pressure at the interface surface is equal to the pressure gauge, okay? All right, that's what it's going to look like, okay? All right, so let's plug everything in. We know that the pressure initially, which is the pressure at the interface, is equal to what? Rho GH. And you say, well, how do you know that? All right, watch. I have the depth, I have the density, and I have G, which is gravity. So I can find, now look, y'all, we know what the pressure is way up here. This up here is atmospheric, unless it tells you otherwise, okay? So that's atmospheric pressure, all right? We know that. But what's the pressure right here, okay? And notice it says what? It says, what is the gauge pressure? Yeah, what is the gauge pressure? Not just the pressure of the fluid, but the gauge pressure is anything above atmospheric, okay? All right, so let's think about that. So, how do we find that then? Well, we look at the density of the fluid, and we use this equation right here. And so I can't write. Rho GH, which is equal to 600 kilograms per meters cubed, times G, which is 9.8 meters per second squared, times the height. Well, the oil was 0.12 meters deep. And what do we get? Well, let's just double check our math here. So we got 600 times 9.8 times 0.12. And we get 705.6 PAs. So we get a pressure of, let me just write it right here, 705.6 pascals. And let me come down here. 705.6 pascals, which is a Newton meter. And you say, how in the world do you get that? Okay. You got a kilogram meter per second squared, which is a Newton. And then you've got to get a Newton per meter squared. Well, a kilogram meter per second squared is a Newton, and a meter over a meter cubed reduces to meter squared, so you have newtons per meter squared, which is a pascal. Okay? And so our gauge pressure, because it's the initial pressure minus the pressure at the surface, which is equal to gauge pressure, pressure gauge, and that is going to be that right there. Okay? That's what it's going to be at the interface. Okay? All right, now let's look at part B. Because if you put the gauge right there, that's what it's going to read. All right? All right. What is the gauge pressure at the bottom of the barrel? Okay. Well, the gauge pressure at the bottom of the barrel, let's just go to a clean slide. So we've got what, 10B? That was 10A. Did I write 10A on that? A, there we go. 10B. So, well, what equation do we, well, to find the pressure on the surface, which could be the absolute pressure, is equal to the pressure, the gauge pressure, plus what? Atmospheric pressure. Okay? So to find gauge pressure, pressure gauge, and by the way, pressure surface can also be pressure initial. Okay? All right? So to find the gauge pressure, then we solve it and we do what? We say the pressure initial, or surface, minus the pressure atmosphere. So the pressure gauge at the bottom of the barrel is what? Well, how do we find that? Okay, guys, you've got to take into consideration the depth of the fluid, and it says that it's on top of water, right? Yeah. Floating on water. And by the way, you don't take the depth of the water. In other words, you don't start at 0.12 and subtract from 0.25. You don't do that. You take because you got to understand, gravity's pulling on all that fluid, so you got to take the whole thing. All right, so how do we find that? Well, we know that the initial pressure was what? Well, we've already calculated 705.6 PA. Then what is the pressure? What is the pressure due to the depth of the fluid? Well, the pressure due to the depth of the fluid is equal to what? Well, it's plus 1 times 10 to the third kilograms per meters cubed times 9.8 meters per second squared times 0.25 meters. Okay? 0.25 meters. And so that comes out to be what? The pressure gauge is equal to 3155.6 pascals, or you could say it this way, or 3.1, how did I write it? Yeah, 3.16 times 10 to the third PAs, or you could actually say 3.16 kilopascals. Okay, you could write it that way too, or 3.16 kilopascals. Okay, all right. Okay. Okay. And that's number 10. All right, hang on, I'll pause a minute. Let's look at number 31. And this is still chapter 12. We're on page 389. Okay. All right, we got a rock with a density of 1,200 kilograms per meters cubed. All right, so we got a rock, and the density of the rock is 1,200 kilograms per meters cubed. Okay. All right. And it's suspended from the lower end of a light string. Okay. So we got a rock and it's hanging here. All right. And when it's in the air, the tension in the string is 28 newtons. Because we have tension going up. And so the tension is equal to 28 newtons. We could also call that the weight. All right. So it has a tension of 28 newtons. You say, well, how do you get that? Well, look, y'all, the sum of all forces is equal to 0. It's not accelerating. So what forces do we have at work? Well, we got mg and we got tension. So T minus mg is equal to 0. So T is equal to mg, which can be weight. Okay, so you can say the weight. So that's actually the weight of the rock. All right. Now, what is the tension in the string when the rock is totally immersed in a liquid with a density of 750 kilograms per meters cubed? So we take a container here, okay, and we got it, and we drop it in here, okay, and we suspend it in a fluid. And the density of the fluid is equal to, and I'm just going to write FL, 750 kilograms per meters cubed. Okay. So we want to know what the tension in the string is. So now we want to know what this is. This is tension suspended, question mark. All right. What is the tension when it's suspended into the fluid? Okay. All right. Or the liquid. Okay. Well, first of all, we need to remember too is how do we find the buoyant force? Okay. All right. And we also need to do what? We need to find the volume of the rock. All right. We need to find the volume of a rock. 1 second. Okay. I forgot this one thing. We got the I need to finish my free body diagram. We've got the tension in the string. We've got weight. We've got mg, which is weight. That's weight, y'all. And we also have what? We have the buoyant force too, don't we? We have Pascal's principle, don't we? Archimedes' principle. Pascal too. Pascal's law. All right. Now watch. Okay. So, now is the object accelerating? Well, no, it's not. But it does have weight. It does have weight pulling it down. So we know what? We know that the tension plus the buoyant force should be equal to what? The weight. Because remember, buoyant force, y'all, is basically what? When you submerge an object in a fluid, that the buoyant force will be equal to the weight of the fluid that is displaced by the object, okay? So the buoyant force is that upward pushing force, and by the way, it is upward. It's not downward, it's upward. So your buoyant force, I know I drew an arrow there. Let me make sure you see that. It's an upward force, okay? And we define it by whatever the volume. It's basically whatever the weight of the volume of the fluid that is displaced by the object. Okay, that's what it is. Okay. All right. So then we can find the tension of the string in the liquid or the solution. We'll say liquid. Let me put an L there. Is equal to what? Mg minus what? The buoyant force, right? Yeah. Okay, well then how in the world do we find that? Well, first of all, we got to know what? We got to know the volume of the rock, don't we? Okay, so what is the volume of the rock? Well, let's look at it. Oops. All right, how do we find the volume of the rock? Well, now remember I just did this equation right here. Remember, y'all, that density is equal to the mass divided by the volume. So if I'm going to solve for mass, mass is equal to what? The density times the volume, right? Okay, y'all, let's go right here, and let's take our equation, and now let's substitute this here, and we've got what? Tension is equal to rho times V times G, and so the volume of the rock then, that's capital V, is equal to the tension divided by what? Rho times G. So the tension was 28 newtons divided by the density of the rock, which is 1,200 kilograms per meters cubed, times 9.8 meters per second squared. And so we get a volume of the rock that's equal to 2.38 times 10 to the negative third. So that's 2.38 times, that's an 8, times 10 to the negative third. I hate it when I mess up. There we go. I want to fix it so you can see it. 8 times 10 to the negative third meters cubed. So there's the volume of the rock. Okay, so now we can determine what? Well, we know our densities, we know our force here. So how can we find the tension in the string? Now remember y'all, that we have our equation right here. All right, so remember now, let's look at this. And by the way, how do we define the buoyant force? Well, the buoyant force, I didn't write that equation down either, did I? The buoyant force is equal to what? Rho times the volume times G. And you say, well, where did you get that? Well, I got that from this right here. Okay, I got this from this equation right here. I substitute for mass, and I get volume times G, and then times the density. Okay? All right. Okay? All right. Now, okay? So we substitute, and that's how we find the buoyant force. It's the density times the volume times G. All right, now, all right, let me double check my math here. Yeah, that's right. Okay. Rho times volume times G. Now, okay, so we got our buoyant force equation. So now let's substitute these in. So the tension in the liquid, y'all, I'm sorry I'm going a little slow and backtracking. I just want to make sure I'm doing everything right, my math right, okay? So we substitute here, we substitute in here, and then we substitute in here, and what do we wind up with? Well, we wind up with rho VG minus what? And that, by the way, is the weight. That's from the rock, the mass of the rock. See right here? See right there? That's what that's from, the weight. Okay, minus the rho of the liquid times the volume times G, times the volume times G. Okay? Now look, guys, we can actually do some factoring here. Okay, we can, notice we've got, look, we've got rho VG and we got rho VG. So what can I do? Well, I can factor out the VG. I can do this right here. I can say TL is equal to what? All right, VG times rho of the rock, let me put rock there, R, minus rho of the liquid. Okay? All right, let's plug everything in then. So we got the volume of the rock, which is this right here. And by the way, we could say millimeters. We could say millimeters cubed. Okay? So we're going to say 2.38 times 10 to the negative third meters cubed times 9.8 meters per second squared. Okay? 2.38 times 10 to the negative third meters cubed times 9.8 meters per second squared. And then it's times 1,200 kilograms per meters cubed minus 750 kilograms per meters cubed. And what do we get an answer? Well, we get an answer of the tension in the liquid is equal to 10.5 newtons. Okay? 10.5 newtons. Okay? So again, y'all, you've got to be methodical and you've got to remember how to substitute. It's very, very important. Let's look at number 38. So number 38, still chapter 12, still on, I think, the same page, 389. All right, now. It says water runs, we got two parts, water runs into a fountain filling all the pipes at a steady rate of 0.75 meters cubed per second. Okay, so that's very important to remember that the flow rate, okay, the flow rate is 0.75 meters cubed per second. Okay, that's the flow rate. All right. And how do we get flow rate? Well, flow rate is equal to area times volume. All right? All right. Okay. Now, what you need to remember, too, this is constant. All right? This is constant. That's going to really help us out in the equations. I guess I need to also draw this. Don't really. This one, I guess, you got water running into a fountain. I guess you could just have a pipe. You got a little fountain here. Okay, like that. And the water's, coming in like this, okay? All right, now. Okay, so it tells us what the flow rate is, and the flow rate, as I said a minute ago, if you take the cross-sectional area times the velocity, then that's going to be equal to what? Your constant flow rate, ain't it? Isn't it? Excuse me. Meters cubed per second. So if I want to find the velocity, then all I got to do is what? I got to say the velocity is equal to 0.75 meters cubed per second divided by the area. And by the way, this is the cross-sectional area, okay? and it's the cross-sectional area of a pipe, okay? All right, so that equation is going to be a little bit different. So the cross-sectional area of a pipe is equal to pi times diameter squared over 4, okay? All right, that's the cross-sectional area of a pipe, and you need to look that up, and you don't need to just, go from off the top of your head, okay? Okay, so let's plug everything in. 0.75 meters cubed over seconds divided by, all right, so we got pi times the diameter of the pipe. Oh yeah, did we get the diameter? I think I overlooked that, okay? 4.5 centimeters in diameter. So the diameter of the pipe is 4.5 centimeters, which is 0.045 meters. Okay, don't forget to convert that. Okay, don't forget to convert it to meters. And now we can plug it in, so it's pi times the what? You can put your 4 right here if you rearrange everything, because it becomes a complex fraction. So you got 4. Can everybody see that? Let me clean that up a little bit. The velocity is equal to 4. Now you say, where'd you get that? All right, go right here, guys. Go right here. Remember, the area substitutes there. And look at what you got. You have a complex fraction. So when you can rearrange it, you can do this right here. It's perfectly legal. So it's 4 times pi, and the diameter is 0.045 meters, and that is squared. Now that's velocity, okay? That's the speed, and you get 471.57 meters per second. Okay? 471.57 meters per second. So that is the speed at which it comes out of that diameter pipe. Now, let's look at 38B. That was 38A. Let's do 38B now. So 38B, at what speed will it shoot out if the diameter is 3 times as large? So if you take the diameter, so we want to know the speed at 3 times diameter. Well, okay, if the diameter is 0.045 meters, right? Okay, and that's times 3, then you get what? You get a diameter, okay, of 0.135 meters, okay? All right, now, we've got to remember something, that the flow rate is constant, okay? So what does that mean? Well, if we go back and look at our equations for fluid flow on it's equation 12.10. It's what we call our continuity equation of an incompressible fluid, and that's very important you understand that, incompressible fluid, okay, which is equation 12.10. We have this equation right here. We have the cross-sectional area of the pipe times the initial velocity is equal, and that's initial, or 1, times the cross-sectional area final, or 2, times the final velocity. And if you want to use 1 and 2, that's fine, okay? Now, remember, the flow rate is constant. Okay? All right? Flow rate is constant. Well, what does that got to do with anything? Well, it's got a lot to do with everything. Since the flow rate is constant, y'all, we don't have to concern ourselves with area. And you say, well, why? Well, because it, since the flow rate is constant, area is not important. And you say, well, now wait a minute. You just said area. Well, okay, guys, look. If you look at the cross-sectional area of the pipe, it's what? The cross-sectional area of the pipe is pi times diameter squared over what? 4, right? Okay? Yeah, it sure is. Okay? Well, all right, look, guys, this is constant and this is constant. Okay? These two values are not going to change. So maybe I should say it this way. Area is important, yes, but the ratio, the only thing that's changing within our equation for cross-sectional area is the diameter, okay? These values right here are not changing, okay, because they're constants. So I can rewrite the equation this way. I can say the diameter initial squared times the initial velocity is equal to the diameter squared, and that's a d, by the way, final times the final velocity. Oh, you can't do that. Oh, come on, guys, you can too. Because these values don't change, okay? They're not changing. The only thing that is changing, I mean, guys, look, you can put it in there and do the math. You're still going to get the same answer we're fixing to get, okay? But I'm telling you guys, you need to look for trends like that, because these values don't change, okay? So I don't need them. All I need is the diameter squared, okay? Because that's what is changing. So we're looking for what? The final or 2? Maybe I should have used 1 and 2. Keep everybody happy. 1 and 2. Does that make everybody happy? So then the velocity 2 is equal to what? Well, it's d1 v1, and that's squared, divided by what? d2 squared, right? d2 squared. Okay? Is that going to mess everybody up if I change in midstream? I hope not. Let me fix it. I didn't mean to mess you up. Okay, so 1, 1, 2, 2, 1, 1, 2, 2. Okay? All right. So there's our equation. So V2, and actually what I should have done is I should have pulled the V2 out, or excuse me, the V1 out, like this. V1. Okay. All right. So let's just plug everything in now. So diameter 2. Did I write that right, or did I write it upside down? Dadgummit. So V2 is equal to D1, yeah, D2 over, yeah, I did it right. D1 over D2. I did it right. Okay. So we've got D1 squared, which was what? 0.045 meters squared, over, and by the way, you could do the whole thing and then square it. You could do it that way. 0.135 meters squared, or what I was saying is you could just do the whole thing and square it. It's the same difference, okay? Times the initial velocity, which is 471.57 meters per second. And so we get a final velocity of 52.4 meters per second. 52.4. All right, now, does that make physical sense? Well, of course it does. Well, why? Because the diameter of the pipe changed. Okay. I mean, have you not ever noticed if they want to increase the speed of the water coming out, one of the things you can do is change the diameter of the pipe. If you want it coming out fast, you go from a large pipe to a smaller pipe. If you want it coming out slower, the other way around. Okay. Notice how the diameter increased, the speed decreased. Okay. The diameter increased, the speed decreased. Okay. Inversely proportional, isn't it? Okay. Now let's look at number 47. And this is still chapter 12, and it's on page 390. Okay. So it says, what gauge pressure is required in the city water mains for a stream from a fire hose connected to the mains to reach a vertical height of 15 meters, okay? Assume that the mains have a much larger diameter than the fire hose, okay? All right, so, well, let's draw this. So we got a person with a fire hose, okay? And they got a fire hose here, and there's the hose going down, all right, on the ground. All right, now, and so it is shooting to a height of 15 meters. So this height right here is 15 meters. We could actually say Y final is 15 meters. Y initial is 0 meters. All right, now remember when we taught, when we were back in kinematics and we were looking at projectile motion and we were looking at the kinematic equations for projectile motion. Remember that we said when an object, and by the way, that stream of water, that fire hose, that's like a projectile, okay? So in actuality, if you think about it, from the starting point, the velocity of the water has to be 0 meters per second in the y direction because it starts at the ground. It starts at 0. And now you say, well, wait a minute, it's going out this way. I'm not talking about x velocity. Notice it says vertical height. That's the key there. It says how much pressure, what's the gauge pressure required to get it to 15 meters vertically. So when it reaches that maximum height, guess what the final velocity is going to be? Well, the final velocity at maximum height has to be 0, y'all. It has to be 0 meters per second because it's in the y direction. It's not going up any further, okay? 15 is it. It goes in the y direction, in the y. Let me put the y on there. Y direction. That's real important, okay? Very, very important. So, in actuality, this is a Bernoulli's equation. Now, remember that Bernoulli's equation only works for incompressible situations, incompressible fluids, okay, materials, particularly fluids. So, let's look at Bernoulli's equation. So we have what? So we have pressure 1 plus what? Rho GY1, rho GY1 plus 1/2 rho V squared. And you say, well, what in the world is this? Well, those are actually the potential and kinetic energies, okay? Is equal to, now this is Bernoulli's equation. You can go, it's on page, well, if you look at the end of the chapter on the summary, you can see it listed, well, shoot, I thought they had it, yeah, there it is. Yeah, page 385, okay, it's equation 12.18. All right, it's equal to the pressure 1, that's pressure, not rho, plus, 2, rho GY2 plus 1/2 rho velocity squared 2, right? Okay, so now let's just go through here and let's cancel some terms out. Okay, let's cancel some terms out. Okay. Well, look, we're starting at an initial height of 0, so that term's gone. And we're starting at an initial velocity of 0, so that term's gone. Since it's going to a maximum height, and in the y direction at maximum height, if y'all remember when we talked about projectile motion, the parameters of projectile motion, if y'all recall, that when you reach maximum height in the y direction, there's 0 velocity. So that term is gone. So let's look at what we're left with. We're left with what? P1 is equal to what? P2 plus rho GY2. Now, y'all, does that make physical sense? Well, of course it does. Of course it does, guys. Come on, think about it. It has to, because there's no initial and final velocities in the y direction. When you start at 0, 0 is 0. And when you reach maximum height, velocity at maximum height in the y direction, 0. Okay? So again, guys, that's why you need to draw it. And you need to physically think about what's going on, okay? Because remember, y'all, we're talking about the y direction, okay? We're talking about y direction. I know I keep saying that, but I want you to get it, okay? Now I got to do a little tweaking here, and we need to try to figure out, because we've got to find gauge pressure. Now remember what gauge pressure is. That is the pressure that is above atmospheric pressure, okay? And typically when gauges are calibrated, they calibrate out atmospheric pressure. Okay, they in other words, when you check the air on your tires, they are negating the effect of atmospheric pressure on that tire. Okay, that is subtracted out. Well, why? Well, because atmospheric pressure on the surface is going to be the same no matter, whether you got 150 psi or 75 psi or 35 psi. The amount of atmospheric pressure at a given location is going to be the same regardless of how much pressure is inside the tire. So you really don't need atmospheric pressure added to your gauge. So you just calibrate it out. Okay. In other words, you measure atmospheric pressure and then set that line at 0 and then measure from there up. So in this case, y'all, when we look at it, we can actually say that P2 is equal to pressure absolute. Okay? And so let's solve now for gauge pressure right here. And so we'd say P1 minus pressure absolute, and pressure absolute is the total pressure. Okay? So if you take the total pressure and subtract out atmospheric pressure, what are you going to get? Well, you're going to get gauge pressure, and one can be atmospheric pressure. And does that make sense? Well, yeah, but y'all, because you're right here at the surface. So one can represent, now here again, y'all, you got to think conceptually, look at your drawing at surface level, which is 0 meters, we're on the surface, then that's atmospheric pressure. So atmospheric pressure minus absolute pressure is gauge pressure, okay? Is equal to what? Rho GY2, okay? All right? Rho GY2. So this right here gives us gauge pressure. Atmospheric minus absolute is gauge pressure, okay? All right, now, so how do we find it? Well, I don't know atmospheric, and I don't know. No, we don't need that, y'all. We've got the water and the gravity, and we got the height. So let's plug everything in. We got P1 minus PA is equal to what? Well, let's see. The water has a density. The water, and I didn't write that down, but y'all, that's one you should memorize, okay? Because you use it so many times. And if you've had chemistry, you already know that. All right, 1,000 kilograms per meters cubed. So we're looking at water in a fire hose, so it's 1,000 kilograms per meters cubed times 9.8 meters per second squared, right? Times the height. Well, how high was it going? Well, we've already determined it was 15 meters. And so P1 minus PA is equal to a value of 1.47 times 10 to the what? Times 10 to the 5th PA. Okay. So that's what my gauge pressure, and this right here is the same as that, gauge pressure. Okay. So that gives us, because atmospheric minus absolute gives us what? Gauge pressure. All right? All right. I hope this helps.